Alright, welcome back, mathematicians. In this video, we're going to look at several examples of how to use the process of integration by parts. Following along on your packets, this would go under example 1. Suppose you had to integrate the product of x times cosine x dx. How can we approach this? First, you probably want to ask yourself, well, why couldn't we do u substitution? It's always a good idea because eventually we're going to have a bunch of different methods for integration, and choosing which method is appropriate and which context is going to be an important skill. And you'll notice u substitution doesn't work here because there's no function or expression and its derivative somewhere else in the problem. I see an x there, but there's no x and its derivative. Because, well, at least that doesn't cover the rest of the problem. We're still stuck with a cosine here. And similarly, the cosine x, there's no negative sine x floating around or even sine x. So u substitution is not going to work even if you chose different items. But what will work is integration by parts. So when we're doing integration by parts, you want to keep that formula in the back of your mind. It's right above on your paper, but I'm just going to write it down again. The formula we eventually use is uv minus the integral of v du. Now this works provided that we're integrating something that looks like the integral of u dv. Okay, you don't need to write this again, but I just recopied the formula to show you what we're after. So what we want to do is come up with a clever substitution where something in our original integral represents u, something in our original integral represents dv. We can look at these as a product, u times dv, if you will. So what am I going to select? Well, we already said above that we want to choose for our u something that differentiates to 0. That's going to be x. If you chose cosine, if you take derivatives, it goes to negative sine, then it goes back to cosine, back and forth. It doesn't ever go to 0. So it's not a good choice for dv. Then we have to cover the rest of the integral with our dv choice. So I'll choose dv to be cosine x dx. So what's this little box I drew to the right? That's how typically I was taught, and I think it's a nice little way to organize your information. But you choose your u, whatever your u is, write that above. So in this case, our u is x. And whatever your dv is, you're going to write that down in the bottom right. dv is equal to, in this case, cosine of x dx. And then the way this little chart works, you can put a box around it if you want, but you don't have to, is that when you're going from top to bottom, when you're going down, you're differentiating or taking derivative. And when you're going from bottom to top, you're integrating or doing anti-differentiation. Okay, so to fill out the rest of this box, if I differentiate here, I get du dx is equal to 1. And then if I wanted to solve for the du, I would bring the dx to the other side. So I'm just going to do that in one step. Again, the derivative would be du dx if I'm taking derivative with respect to x, which would equal 1, but then I just brought the dx to the other side. Similarly here, if we integrate, integrate dv, you get just v. That's how we get to v. And if we integrate that right-hand side with respect to x, the integral of cosine is sine. And you could check yourself real quick because the derivative of sine is cosine, so that works. And now with all this information set up, it's just a matter of plugging in the proper expressions to the formula. So our uv minus v du, or the integral of v du, becomes, well, u is x, so that's just x. V is sine x, so x times sine x, minus the integral of v, which is sine x, du, which is just 1 dx. And we can compute this. This would equal x sine x minus the integral of sine x would be cosine x, but it would be negative cosine x, so then this minus sign in front is just going to become a plus cosine x. And then don't forget, this is an indefinite integral. You will lose a point or more if you don't put plus c, some constant at the end. And that's the result of our first integral for integrating by parts. Next, we'll look at example 2. Okay, let's look at example 2. In this integral, we want to integrate the integral of x squared times e to the x dx. And in an integration by parts, which as you start to look at more of these, you'll see these generally work when you have two functions multiplied together and you don't see an immediate u substitution. There's no u substitution here that's obvious. Yes, we could use x squared as u, and then du would be x, but this x is stuck in the exponent. So picture like a du in the exponent, that's not going to work for integration. For integration with u substitution, the du needs to be in the numerator and not inside of any other functions. So that's not going to work. So we try by parts, and we make our chart here, and we want to make a choice for u and a choice for dv. Our choice for u, something that differentiates to 0, here is x squared. Our choice for dv is going to be the rest, something that we can integrate easily, and e to the x fits that criterion, so that's it. Then we take derivative, du dx would be 2x, and then I'm going to bring the dx to this side. We integrate over here, and we have e to the x. That in place, we can plug into our formula and say that this integral is equal to u times v, x squared e to the x, minus the integral of v times du. I'm going to bring the 2 on the outside, dx. Now you'll notice this integral here, in the last example it was easy to do once we did integration by parts. But in this example, the integral of x times e to the x, let me just write it a little neater. Usually we write it like this, 2 and then x e to the x. It's not easy to compute. This doesn't have an obvious answer, and it's also not a u substitution. So what can happen, similar to when we did L'Hopital, sometimes you needed more than one round to make it work. Here we're going to need integration by parts again. So we set up another chart, and we're going to do this second integral by integration by parts. So in our second integral, I'm going to make a choice for u and a choice for dv, e to the x dx. We differentiate here. This is du dx is 1. I bring the x to the other side. And this is v is e to the x. And now for this portion, I'll circle it in black, I'm going to substitute the integration by parts formula. So we have x squared e to the x minus 2, and then I'll do parentheses, and then we have uv, which is x e to the x, minus the integral of v, which is e to the x, du, which this time is just 1 dx. And now we can integrate this, and when we do so, we get a final answer, which is going to be 2, oh, I'm sorry, not 2, let's erase that. It's going to be x squared e to the x minus, and then we have 2x e to the x, and then this minus sign gets distributed, so just be careful there. So that's actually going to be a plus. Or not that one, I'm sorry. The next one's going to be a plus. So this is a minus sign because this is minus here, but it gets distributed. And it'll be plus e to the x plus c. This is an acceptable answer as an open-ended question. If you're looking at a AP multiple choice test, there's a chance that they'd write it in factored form. They might take out the e to the x of all these, and then it would be x squared minus 2x plus 1. And they might have read it like that, or this can actually be factored further into x minus 1 squared. So they might even list the answer, third possibility, e to the x times x minus 1 quantity squared plus c. Okay, I would accept all of those. Just be wary for simplification on the multiple choice section. Okay, thanks for watching those two examples on integration by parts.